Okay, Assalamualaikum and good morning, everyone. Okay, so for today's lecture, you have learned about electrical stimulation model last week. So this week we are going to look at how we can apply solid mechanics model on biomechanics. Okay, so today's lecture is about biosolid mechanics. At the end of this lecture, uh, you will be able to understand the application of solid mechanics in modeling a biomechanics system and solve and analyze various solid mechanics model of biomechanics using COMSOL multiphysics. So the application of mechanics in biology, we call it biomechanics. So in biomechanics, there are two types. So we have solid mechanics and also fluid mechanics. So the concept, these two basically the derivation of the equations are almost the same, are almost similar. But the difference is that in fluid mechanics later, it describes about fluid flow. So the equation will be slightly different to accommodate fluid properties like either laminar flow or turbulent flow. But for solid mechanics, um, we assume that the solid doesn't move, or the particles doesn't move um, smoothly as fluid. Okay, so in solid mechanics deals with the deformation, okay? Deformation of solid bodies under various loads. So if you can imagine your parts of your body, for example, like soft tissues. So soft tissues are like skins, muscle, ligaments. So for example, your muscle, your hand muscle, your bicep or tricep, when you hold something, then you will stretch your bicep. And then when you release a thing that you hold, then your bicep will be released or relaxed. So your muscle basically can be treated as a solid that is deformed or stretched when you apply some loads, and then will return to itself. I mean, to the original form when you release the load. And you can also study the mechanics of devices such as hip implant or hip joint or prosthetic device. So prosthetic device is something that replace parts of your body that missing. For example, if you lost your hand, then you wear a prosthetic hand, for example. So the basic of solid mechanics is always related to the strain and stress of a material. So the deformation of solid can be measured by using the strain, or in solid mechanics we call it strain tensor. So a tensor is basically a matrix. Okay, so maybe if you still remember in finite element method. So when you learn finite element method, we assume that each node will have displacement in x direction, displacement in y direction. So that's why your matrix sometimes becomes 4x4 matrix, because you have x and y direction for one node and another node x and y direction as well. So you get a 4x4 matrix. And that is for 2D cases. But for 3D cases, you will have uh, x, y, and z direction. So you will have 6x6 matrix. But in solid mechanics, we also have strain um, and stress. Okay, so strain, we also have a strain in the shear. Okay, the shear direction. If you still remember finite element again, or solid strength of materials, you learn about shear stress or shear strain, and this shear strain and the principal stress or principal strain or normal shear or normal strain can be described, all of them cumulatively, in a tensor form or in a matrix form. Okay, So the solid deformation basically describe the change of shape of materials. So assume that at reference state or at time 0, maybe the shape is something like this shown here. And then after you apply some load, and at time t, at a deformed state, then the shape will be changed slightly. So we can measure this change of shape using strain tensor. So the derivation is basically comes from this figure, okay? But the derivation is kind of long. So of course, I cannot show you here because the derivation for solid mechanics itself is actually a 1 semester course, okay, for you to understand in detail. But here I'm going to show you only the basic principle or basic concept only. So we have a stress on a rigid body. So we also have stress and strain. Just now it's strain, now it's the stress. So the stress is not uniformly distributed over the body, okay, or over a point of in a body. And because of that, we can describe stress also using a tensor. So a tensor is a matrix. So here it's a 3x3 matrix. So if you look at this tensor, we have sigma xx, sigma yy, and sigma zz. And we also have the tau. Okay, so the tau is the shear stress, tau xy, xx, and so on. So all of this can be described in one symbol or one matrix, okay, or we call it tensor. So the normal stress is perpendicular to this box. So this box is a one tiny particle inside the big materials, okay. So the normal stress on from the box, we call it the normal stresses, and then the parallel, okay, the parallel stress, we call it shear stresses. So the shear has on upward direction and also in the horizontal direction. So that's why we have 3x3 matrix. So the most important thing about solid mechanics is the constitutive law of materials. So if you still remember strength of materials again, you might remember about the Young modulus, Poisson ratio. So all of this describe the properties of a material. So in simulation for solid mechanics, we only need the properties of the materials, either the Young modulus or Poisson ratio. But there are a lot of laws for materials. Okay, so the law that involve Young modulus and Poisson ratio is what we call linear elastic constitutive laws. But in our body, for example, muscle just now, we cannot use linear elastic to describe the properties of a muscle because our muscle, when you apply a load, it will stretch. But when you release the load, then it will return back to its original state. Okay, so it works something like a rubber, a getah. Okay, so if you pull a rubber, then it will stretch, it will elongate. But when you remove the stress or the load, then the rubber will return to original state. So it's kind of the similar mechanism to our muscle, okay, or basically to our to our body or to our tissue. Skin also works like that. Muscle, ligament, and even other tissues in the body like heart tissue, brain tissue, and so on. So this material or constitutive law, we call it hyperelastic. So hyperelastic constitutive law basically applied for rubbery type material. And we also have viscoelastic. So viscoelastic is something applied to material that has some form of viscosity. Okay. So let's overview a bit about stress strain curve for linear elastic material. So I hope you still maybe you recognize this figure maybe in one of your subjects. So a material will behave elastically within the OA region. Okay? It will obey Hooke's law. So at this OA region, the material will have the Young modulus and Poisson ratio that relates linearly the stress and strain. And after this point A, we call it the proportional limit, then the material will not behave linearly, okay, until A and B. When it reach B, it will reach a elastic limit, okay, or a yield point. So after this point, then the stress, the material will not return to its original state after you release the stress. So after the point B, then the material will behave like a plastic, plastic behavior. Like it forms a necking. If you still remember a straw, if you pull a straw, then it will start to form a necking in the middle. So after the point D, so D is the ultimate tensile strength where the maximum strength or the maximum stress that a material can handle. And then after this point, then the material will start to fracture, okay? Will start to break. So the important thing is this linear elastic region. So we sometimes use linear elastic region in simulation for human body if we assume that the strain or the strain of the materials or the strain of the tissue is not big, maybe less than 1%. Okay, so if the tissue strain or the displacement of tissue is very very small, then we can use linear elastic constitutive law. So linear elastic constitutive law basically relates the stress and strain using Hooke's law. So stress, sigma ij. So why ij? Because it's a matrix. So it has 3 by 3 elements, okay? 3 by 3 matrix. And strain also is a 3 by 3 matrix. And the symbol C here represent the elasticity tensor, or we call it a stiffness tensor. So C basically contains the Young modulus and Poisson ratio, or basically the material properties of the material. And the CIJKL, is a fourth order tensor or have 81 elements. Um, because we are using software, so we don't need to know the elements inside the 81 elements, but we only need to know the Young modulus and Poisson ratio. So for elastic material, linear elastic material, we have, as I said, we have Young modulus and Poisson ratio, but we can also use other parameters or other modulus. For example, we have bulk modulus and we have shear modulus and Lame's parameter. First parameter, lambda, and P-wave modulus. So you can refer this in Wikipedia. So basically what we need is that we only need any of these two modulus. Okay, so for example, if we have shear modulus and Poisson ratio, then we can know the other things like E, K, lambda, and M. We only need to know two of these six. Okay, we don't need to know all six because the formula to calculate the other moduli actually depends only on two elastic modulus. Okay, so for example, if you have E and V, you can get K, G, lambda, and M by using formula. So the formula you can refer to Wikipedia, but in our course, we don't need to know the formula. Okay? So this is about hyperelastic materials now. So hyperelastic material usually describe the properties of a rubber. Okay, so material like rubber can be stretched up to several times. Okay, can be stretched and then release, stretch again and release many times, but it will still maintain its original shape. Okay, so from this figure, the elastic region is very large. Okay, so when you apply a very small stress, then the strain becomes very big, but it can return to its original state. So hyperelastic material usually used in our to describe our body's material properties such as skin, aorta, and muscle. So for hyperelastic materials, we cannot use anymore the stress-strain relationship uh, similar to elastic material. but we use a strain energy function or strain density energy function. So stress equals to the derivative of strain energy function over strain, okay? Derivative of strain. So in finite element software, the model has been included in the software usually, okay? So you don't need to write your own code. So there are a lot of model describing the hyperelastic materials, okay? So usually in finite element software, we will have a neo-Hookean hyperelastic material model, Monet-Rivlin hyperelastic model, Ogden, and if you are daring enough, you want to write your own model, then you can write in the user-defined code, okay? User-defined code. Okay, so we can now go to tutorial. So tutorial, so in this tutorial, basically it studies about the shear in the myocardial tissue. So myocardium is our heart tissue. So simulate the myocardial shear experiment below in console using Monet-Rivlin constitutive law with material parameters C1 and C2, and rho is the density. Assume the myocardial sample is a cube of 3 times 3 times 3 millimeter. So this is your myocardium. You apply a shear on the top surface. So it will form like, dia akan macam terslide, okay? Sliding. It looks like a kuih lapis. Sedapnya. And then you can plot the force versus shear. So you get something like this graph, okay? It's not linear. It's like quadratic, okay? Okay, so let's follow this tutorial. If you have console, you can open up your own console. Okay, so we start by choosing 3D, solid mechanics, and stationary study. So model wizard, 3D. So solid mechanics, you can find it under structural. Here, solid mechanics. Or you can type in the search. So double click solid mechanics. Oh, namanya. Okay, and then go to study. Then choose stationary and then click done. And then we can start by drawing the block, the geometry. So the size is 3 by 3 by 3 millimeter. And we draw at the corner 0, 0, 0. Okay, in geometry, right click, you choose block. Or you can find a block in geometry tab on top. Just choose this block, okay? And then here, in the size and shape, just write 3e minus 3, represent 3 millimeter. Or you can write in bracket, okay? So bracket, just put millimeter and close bracket, but you must use square bracket, okay? So there are many ways you can do this. And to check, you can just build selected. So you get a cube, and you can make sure the unit, okay? So it's 10 minus 3 meter. So it's in millimeter. Then we can set the hyperelastic material model. So firstly, we go to solid mechanics. And then by default, it will give you linear elastic material. So we don't want linear elastic material, we want hyperelastic. So what we need to do is we right click solid mechanics and go to this material models and just choose hyperelastic material. So in COMSOL there are a lot of material properties, but for biomechanics we usually focus on hyperelastic material, sometimes linear elastic and sometimes non-linear elastic, but most of the time it's hyperelastic material. So there are other materials. So I don't know the other one, the other materials like shape memory alloy. So you can try by yourself lah if you are interested. And then when we choose hyperelastic material, so by default it doesn't give any domain in the domain selection. So what you need to do is you just go to the cube and just click, okay? So now in the domain selection, it will put number 1. So number 1 here represent the domain 1 or the cube. And if you go to linear elastic material 1, so word overridden is written, meaning that the material of this cube is no longer linear elastic. It will follow hyperelastic material. So in this window for hyperelastic material, you can choose what material model that you want. So here in the material model, we have COMSOL has a lot of material models for hyperelastic. So we have Neo-Hookean, San Vernon Kirchhoff, Muni-Rivlin. So Muni-Rivlin, there are 3 types, 2 parameter, 5 and 9 parameters. We have Yo, Ogden, Storacus. I don't know what is Storacus, Varga, Aruda, Boyce. I don't know again, Blood, Cow, okay, and so on. And here, user defined, you can write your own code if you have a different model that doesn't include it in COMSOL. So for this simulation, we choose Moni-Rivlin 2 parameters. So why 2 parameters? If you look at the question again, it already says Moni-Rivlin constitutive law with C1 and C2. So there are only 2 parameters given, C1 and C2. Sometimes maybe question maybe give you more than 2 parameters, but so far tak tanya lagi lah. So far I will only use 2 parameter model. Okay, so C1 and C2. So after we choose the hyperelastic material, we can now set the material parameters. So in hyperelastic material, it will give you 2 parameters, C10 and C01. So here, by default, it will give you from material. So you can input your own value by putting user defined, okay? By changing the drop-down menu to user defined. And then just put the material properties here, 1e power 4 and 2e power of 3. So 1e4, 2e3. And then we have the density. So density is 1000. So density is 1000. So here I forgot to put the bulk modulus. The bulk modulus usually put 10e power of 7. Okay? 10e power of 10, sorry. So we just put here 10e power of 10. So after we put all these parameters, then we can now set the boundary conditions. So let's go back to the question, what it says. So basically, we apply a shear stress on the top. So we apply a shear stress on the top, but the bottom surface, we fix the bottom surface. So what we need to do is we fix the bottom surface by using fixed constraint. So first, there are no fixed constraints, so just right click solid mechanics and choose fixed constraint here. So fixed constraint and then choose the bottom surface. Okay, so fortunately, the number is similar with lecture notes. Okay, boundary number 3. So what happens is that this surface here will be fixed. It will not move. It will stay at this location. And then we apply the displacement or the shear. Okay, so firstly we need to define this D shear in parameter. Okay, not yet. Okay, it's on the next row. Okay, so whatever, we go to this prescribed displacement. So right click again, right click, and then choose prescribed displacement, and then choose the top surface. Okay, boundary number 4. And then in this boundary, we check all boxes, set prescribed in X direction as D underscore shear. So check everything. Serious, I check everything. Ni go check ni. D underscore shear. Okay, tak pergi try. And then we need to define the D shear in global definition parameter 1. Okay, so in D shear, in the global parameter, this one, global definition parameter 1, we write D shear, expression 0. Then after that, we mesh. So we choose coarser mesh to make the simulation faster. Okay? So here mesh. So by default, it's normal size. So we choose coarser and try build. Okay, so it's quite big. And then we can go to study 1. So study 1. And right click parametric sweep. So right click parametric sweep. And then click plus button, choose this shear. And then write this range. So copy first. So click this plus button and choose this shear. And in the parameter value list, just copy and paste. So this parametric sweep is basically similar to your assignment number 4. Yes, assignment electrical stimulation. So in that assignment, basically it's last semester punya test. So in the test question, it asks you to use parametric sweep to change the location of the ground electrode. So what is parametric sweep? So parametric sweep basically it will do simulation for you by changing the value for the D shear or the parameter that you choose. So for example, here we define in parameters 1 under global definition, we define D shear. So D shear is a parameter, but we want this parameter to change, not only has one value 0, maybe we want the simulation to run parameter for D shear for value 0, value 1, value 2, and so on. So if you, let's say if you have 10 different D shear values, so you need to run 10 different simulations for different D shear values, value 1, 2, 3 until value 10. So you will require to open 10 console, okay, 10 times, and it might use or consume a lot of RAM and consume a lot of computer power, okay, or it will slow down your PC. So by using parametric sweep, we choose what parameter that we want, and then we choose the parameter value that we want the simulation or the console to run. Okay, so in this case, we want console to run simulation for value of D shear for 0 until 0.001 with stepping of 1 e power of -4. So here I think there are 100 or I think 100 of simulation for different D shear values. So to save computer space or computer power, we use parametric sweep. So similar to assignment number 4, if you try it later, the question asks you to change the location of the ground electrode. So you can use parametric sweep instead of using multiple console. And then when you want to plot the result, you have to check. You have to take each results for different simulation and combine them, which is troublesome. But by using parametric sweep, the result will be collected together, okay, in one file. So here we choose this year for different values. And then the disher will apply on the top surface, okay? And then we go back to the tutorial. So after we set the parametric sweep, we compute the simulation. So just go here, compute. So it might take quite a while. Okay, tak start pun. Okay, so we have finished the simulation. So we can analyze the results. So firstly, we want to plot this figure on the left. So the figure here shows the total displacement, okay? So we can go to the default plot, the surface plot. So in the surface plot, by default, it will plot for you the von Mises stress, okay? Solid dot Mises, meaning von Mises stress. So you want to plot the displacement. So just click this button and go to solid mechanics and displacement, and then total displacement. And just click plot. So you get kuih lapis yang kita dambakan tadi. And then by default, COMSOL will give you this deformation plot. But if you disable this plot, then your result will not deform, okay? Your cube will not deform. It will only plot the displacement, assuming that the plot is on the original shape of the cube. So the deformation here is another plot, but by default, it will give you this plot. So by default, if you enable it, then it will show the actual deformation of the solid or of the material when you apply the stress or the load. So here you can play around with the scale factor. So scale factor 1 meaning that it's a one-to-one representation, okay? Meaning that this is the actual deformation. Okay, so make sure you change this when you plot so that it shows the actual deformation, okay? So we got our first figure plot. And then we want to plot this figure on the right, the force against shear plot, the D shear. So in the last column of the tutorial, it asks you to calculate something. So here we want to calculate the force applied on the top surface. Okay, so to do that, we use this derived values, integration, and surface integration. So the force applied on the top surface, okay, so we have the displacement, but we need to calculate the force, okay. So in the top surface, we know the stress already from the displacement or from the shear stress, shear strain, and so on. So to get force from stress, so stress is equals force over area. So to get force, we calculate stress times the area. So we need to know the area of the top cube and then multiply with the stress on the top surface. So we go to the derived value and then we choose integration. So why integration? Because force stress equals to the derivative of force over derivative of the area. Okay, ni formula. So to get force, you need to integrate stress times the area. So the area is a boundary, or is the area of the surface. So we choose integration on the surface. Okay. So we cannot integrate on the volume because we need to integrate on the surface of the top of the cube. Okay. So we choose the top of the cube, and then in the solid in the expression we choose the stress. So the shear just now acting in the x direction. So we want the stress that is acting on the x direction as well. So we need to choose the stress acting on the x direction. So we go to stress, and then we choose this one. Good. Okay. Tengok balik. Solid SL11 under tu. So here solid mechanics, stress, this one. Okay. So we choose this stress. But it should be the same if we choose this stress also. Solid. Oh, sama. Ni lah. Okay, stress tensor local coordinate. Solid SL11. This one again. Okay, so when you choose solid SI11 here in the surface integration, so you need to double check whether you will get a force or not. So here the unit shows Newton, meaning that after you surface integrate this stress, you will get something in with a unit Newton. So meaning that you will get a force value. So here, if let's say when you choose a different expression, for example, if you choose displacement, so here the unit becomes meter cube. So it doesn't give you Newton, meaning that you choose the wrong expression. Okay, so if you choose stress and integrate stress on an area, you will get a force. Okay, so here the unit indicates whether you get a force or not. Okay, so after you choose this, then you just evaluate. So you get a different value of stress according to each of the shear force or shear displacement. Now for this, you can plot the graph. So just click this button, table graph. If you click this button, you get a graph similar to the one in tutorial. Okay, similar to this one, but here it changed the label force and shear. So you can change the label by going to this process table. Okay, here. So here you just change force. So you get force against the shear force. Sabar jap. Okay, that's all for today's lecture. Any question before we end this lecture? Okay, so actually we have one more lecture next week. So next week is our last lecture, and then you have 2 weeks for you to do your project. And then we will do test number 2 on week 13. So next week is week 10. And then 2 weeks for you to do your project or to study. And then week 13, we do our test. Okay, test 2 on Friday. I put already announcement in Kalam. And then week 14, tempo bertenang. And then I want you to present your project on week 15 Monday. Okay, so I don't want to do it everything on week 14 because I also busy on that week. Okay, so if you have no question, see you next week, inshallah. Assalamualaikum. Goodbye.
Thank you, sir.
Thank you.
Yeah.
You,
Thank you, sir.
sir.
Thank you.